Hi students, have a nice day. Let's continue the fundamentals in organic reaction mechanisms. As we have seen that the different displacement of electrons in an organic molecule, inductive effect and resonance effect. Inductive effect is a permanent displacement of electron in the carbon chain, plus I effect and minus I effect. Similarly, in resonance, the delocalization of electron. Resonance means delocalization of electrons. The position of atom is similar. Number of lone pairs and bond pair are similar. Charges are similar. All these things you learned in the 4th chapter. So two type of resonance. One is plus R effect, that is positive resonance, and the second is negative resonance or minus R effect. In positive resonance effect, electron is donated to the ring, and that's why the group become positive. In negative resonance, minus R effect, the group or an atom which withdraw the electron from the conjugated system or a aromatic ring. What is conjugated system? A conjugated system which contains alternative double bond and single bonds. Okay, all these things you know that. Alternate double bonds and triple bonds. Okay, alternate double bonds or triple bonds. Multiple bonds. We can generally call it as multiple bonds. Alternate double bonds or triple bonds in long chain or in the cyclic ring is called a conjugated system. And in resonance effect, two type of groups are there. Plus R group. Okay, positive resonance group. The groups are halogens. Halogens. Halogen is minus I group. Remember that. Halogen is minus I group, but in resonance effect it is positive resonance. Halogens, then OH group, OR group, okay, OR group, then alkyl groups. All these are having positive resonance effect. Okay, aniline. Another one is NH2, lone pair. Then bond R NH NR2 group. Okay, all these groups are positive resonance effect. And minus R effect, minus resonance effect. The groups are COOH. Okay, carboxylic acid group, CHO, C double bond O, that is keto group, cyanide group, NO2 group, CONS2 group, like that. Okay, so these are having minus R effects. And we move to the next effect is electromeric effects. The next effect is, the third effect is electromeric effect. Electromeric effect. And remember that it is a temporary effect. Electromeric effect is a temporary effect. Inductive effect and resonance effects are permanent effects. Okay, they are permanently in the molecule, and that's why the molecule is polarized. You remember that. Okay, inductive effect and resonance effect are permanent effects, and that's why the molecules have polarity. Okay, the molecule is polarized. And electromeric effect is a temporary effect, which means When an attacking reagent comes into the double bond or a triple bond, that is multiple bond, the electromeric effect works. Okay, once again, electromeric effect is a temporary effect. When an attacking reagent comes to a multiple bonds, okay, C double bond to C, C triple bond to C, C double bond to O, C triple bond to N, like that. The attacking reagent comes, the electromeric effect works. Okay, and that's why it is called a temporary effect. In the absence of this attacking reagent, the electromeric effect is cancelled. So only in the presence of attacking reagent, electromeric effect works. In the absence of attacking reagent, electromeric effect do not work. And electromeric effect is represented by E effect. E effect. As like inductive effect is I effect, resonance effect is R effect. So E effect are of two types. One is positive electromeric effect and the other is negative electromeric effect. Okay, are similar to inductive effect and resonance effect. Electromeric effect is also two types. Positive electromeric effect and negative electromeric effect. As you know that what are electrophiles and nucleophiles? Electrophiles are electron loving species and electrophile is represented by E plus. Okay, generally electrophiles represented by E plus. What are the electrophiles? Cl plus, then NO2 plus, CH3 plus. Okay, these are positively charged electrophile. H plus is also an electrophile. H plus. And similarly nucleophiles. Nucleophile is represented by Nu minus or Nu. Simply if it is a neutral molecule, Nu is enough. And if it is charged one, Nu minus. Cl minus, OH minus, Br minus, NH2 minus, RO minus, like that. So electrophiles are electron loving species or electron seeking species. You know that. Nucleophiles are nucleus seeking or nucleus loving, or they try to seek the positive states. So here, when the electrophile comes, the multiple bond electron is shifted in one fashion. When a nucleophile comes, the multiple bond shifted in another fashion. And when a electrophile comes and is attached to the double bond, it is called a positive electromeric effect. When an electron rich molecule, a nucleophile comes, the effect is called a negative electromeric effect. Okay, let's discuss one by one. First of all, positive electromeric effects. Okay, positive electromeric effects. Positive electromeric effects. Electromeric effects plus E effects. And you know that it works in the multiple bonds. Okay, it works in the multiple bonds. Only in the presence of an attacking reagent. Now I take H plus, or you can take Cl plus, NO2 plus, or simply you can take E plus. Okay, electrophiles, E plus. And the electromeric effect is represented by a curved arrow. Curved arrow. When this pi bond is shifted to this carbon atom only in the presence of an attacking reagent, that carbon becomes negative. Okay, that carbon becomes negative. And to that carbon atom, the H plus is attached. So we get CH. Once again, the multiple bond is shifted to one of the carbon atom. That carbon becomes negative. To that carbon atom, H plus is attached. And the carbon which lost its electron become positive. Okay, the carbon which lost it become positive. Here, the electron pair is shifted to an atom. To that, the attacking reagent is attached. That's called it is positive electromeric effect. So, positive electromeric effect is explained or described. The shared electron in a multiple bond is shifted to one of the atom. To that atom, the incoming or the attacking reagent is attached. Okay, so here the electron, this electron shift. A electron shift attacking reagent attached. And that is why it is called positive electromeric effect, plus E effect. Okay, the shared electron pair shifted to one of the atom. To that atom, the attacking reagent is attached. That is called electromeric effect, positive electromeric effect. And the second one is negative electromeric effect. Negative electromeric effect. Here, the multiple bonds. A nucleophile Cn minus, or you can write Nu minus. Nu minus. And this electron rich center is attached to this carbon atom. So what happens? This pair is shifted to that carbon atom. So we have C, a negative charge single bond Cn. Here, the attacking reagent attached to the carbon atom, the electron is shifted to that carbon atom. Okay, this electron is shifted to that carbon atom. To that carbon atom, the attacking reagent is attached. That's why it is positive electromeric effect. Please listen here. Okay, here the shared electron pair is shifted to one of the atom. The attacking reagent do not attach to that carbon atom or do not attach to that atom. Once again, the electron pair is shifted to one of the atom. The attacking reagent is do not attach to that carbon atom. Okay, electron pair is shifted to atom attacking reagent attached to. Another atom attacking reagent attached to. So once again, please listen. In this case, the shared electron between the two atoms in a multiple bond shifted to one of the atom. The attacking reagent do not attach to that carbon atom. Okay, the attacking reagent is attached to the other carbon atom. That's why it is called a negative electromeric effect and is represented by minus E effect. Positive E effect. Positive E effect and a negative E effect. And you should keep in your mind, electromeric effect is a temporary effect. Only it works in the presence of attacking reagent. If the attacking reagent is not there or if the attacking reagent is removed, what happens? The electromeric effect is not takes place. Clear? Next we discuss hyperconjugation or Baker-Nathan effect, or it is also known as no bond resonance. Okay, once again, hyperconjugation, Baker-Nathan effect or no bond resonance. Hyperconjugation is generally a stabilizing interaction. The interaction of CH sigma electron to the pi system or a aromatic ring. Okay, it is a stabilizing interaction. And hyperconjugation is the delocalization of CH sigma electron. Okay, CH sigma electron of an alkyl group attached to unsaturated system or unshared electron in the p orbital. Once again, hyperconjugation is a delocalization of CH sigma electron of an alkyl group is attached to unsaturated system or a p orbital contains unshared electron or the alkyl group attached to the benzene ring. Okay? And when the CH sigma electron is enter into the partial delocalization, the hyperconjugation takes place. Okay, when the CH sigma electron enter into the partial delocalization of the p orbital, hyperconjugation takes place. In order to understand the hyperconjugation, let's take ethyl cation or ethyl carbocation. Okay, so to understand the hyperconjugation, we consider the ethyl carbocation. Ethyl carbocation. And this carbon atom is sp3 hybridized. And this is sp2 hybridized. sp2 hybridized. Okay, let's draw the carbon atom. There are three hydrogen atom. In that, two hydrogen is represented by normal bond and a wedge. And in this case, the hydrogen is attached to the sp3 hybridized p orbit. Okay, sp3 hybridized orbit. Or you can draw only one sp3 hybridized orbit. We just draw the hydrogen atom. Single bond C. It contains two hydrogen atoms. Okay, two hydrogen atoms. This orbital contains two electrons, one electron from the hydrogen, one electron of the carbon atom. And this positive carbon contains an unshared p orbital. Okay, an empty p orbital. So here the electron is delocalized with that p orbital. Okay, the electron is delocalized with that orbital. And this is called hyperconjugation. So once again, the delocalization of CH sigma electron. So very important. CH sigma electron. When it is attached to an unsaturated system or it is attached to an atom or an atom with the unshared p orbital. Unshared p orbital. Okay, let's draw these hyperconjugation structures. Okay, we have to draw the hyperconjugation structure. Let's take this carbon atom. C, H, 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 C single bond C plus and two hydrogen atom. First of all, this CH sigma electron undergo delocalization. Okay, and we get the structure HC, H double bond C, H, H. and that hydrogen which having positive charge. Why? Out of these two electrons, the electron pair is shifted in between the two carbon atom. So here is H plus. Here is plus on the carbon atom. Here the plus is on the hydrogen atom. And the another possibility, this hydrogen participated in the hyperconjugation. So we have a structure H, C, H, H, double bond C, H, H. Okay, when this hydrogen participated in the hyperconjugation, the structure is like this. And another possibility, this hydrogen, okay, this hydrogen participated in the hyperconjugation. We have another structure, double bond C, H, H, and the hydrogen is positively charged. So this carbon having 3 hydrogen atom. Okay, this carbon is attached to an carbon atom which having empty p orbital or unshared p orbital, contains 3 hydrogen. That's why we get 3 hyperconjugative structures. Okay, 3 hyperconjugative structure. Once again I explain. This is ethyl carbocation or simply ethyl cation. Ethyl cation contains 1 carbon 3 hydrogen. Other carbon which is sp2 hybridized and which contains 2 hydrogen and 1 unhybridized orbital. And a CH sigma electron. The adjacent carbon atom having CH sigma electron is enter into the delocalization. And that delocalization is known as hyperconjugation. By sharing the electron to the p orbital of adjacent carbon atom. One structure we obtain. Okay, this is the sharing one hyperconjugative structure. How it takes place? The bond electron is shifted between the two carbon atom. A double bond is formed. This hydrogen is positive, and 2 other hydrogen atoms are there. Another possibility: this hydrogen involved in the hyperconjugation. First, this hydrogen involved, and second possibility is this hydrogen involved in the hyperconjugation. The structure is this one. And this hydrogen, okay, the third hydrogen involved in the hyperconjugation, we get another structure. So 3 hydrogen to the adjacent carbon atom. We have 3 hyperconjugative structure. When the number of alkyl group increases, the number of hyperconjugative effect also increases. Okay, number of alkyl group attached to the sp2 hybridized carbon atom, the number of hyperconjugative structures increases. Okay, let's consider another one. Okay, this is ethyl carbocation. Next we consider the isopropyl carbocation. This example is given in our textbook. Isopropyl carbocation is not given. Next is isopropyl carbocation. CH3 twice CH plus. Okay, the first CH3 and the second CH3. A positive charge, hydrogen, 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 hydrogen. Okay, the possibility. First, this hydrogen involved in the hyperconjugation. What is the structure? H, C, H plus, double bond C, H, C, H, H, H. Okay, this hydrogen involved in the hyperconjugation. One structure is obtained. What about this hydrogen? So that hydrogen involved H plus C, H, H, double bond C, C, H, 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 H. Okay, when this hydrogen involves, second structure obtained. What about this hydrogen, the third structure obtained? H plus, double bond C, H. Okay, these three hydrogen involves, three hyperconjugative structure is obtained. And another three structures from this carbon atom. This hydrogen involves one structure. This hydrogen involves another structure. This hydrogen involves another structure. So totally 6 hyperconjugative structures. 6 hyperconjugative structures. How many hyperconjugative structures? 6 hyperconjugative structures. In ethyl carbocation, 3 hyperconjugative structure. Isopropyl carbocation, 6 hyperconjugative structure. And you can practice CH3 thrice C plus. Can you imagine how many hyperconjugative structure? Okay, how many hyperconjugative structure? 9 hyperconjugative structures. 9 hyperconjugative structure. Okay, 3. One CH3 contributed 3 structure. Another CH3 contributed 3 structure. And the third CH3 contributed 3 hyperconjugative structure. Totally 9 hyperconjugative structure in tertiary butyl carbocation. Now we come into the stability of the carbocation. What is the order of stability of carbocation? It is methyl carbocation is less stable than ethyl carbocation is less stable than isopropyl carbocation is less stable than tertiary butyl carbocation CH3 thrice C plus carbocation. Can you explain the reason? Okay, can you explain the reason? The simple reason. CH3 plus, now hyperconjugative structure. Okay, CH3 plus, now hyperconjugative structure because it is not connected into the CH bond, the adjacent CH bond. Here, 3 hyperconjugative structure already written. Okay. CH3. Just now we had draw the 3 hyperconjugative structure. This contains 6 hyperconjugative structure. The possibility is 6 hyperconjugative structure. And tertiary butyl carbocation has 9 hyperconjugative structure. So number of hyperconjugative structure increases the stability of the unsaturated system or the alkyl group which is attached to the benzene is increases. Okay, so very important thing, hyperconjugation. Similarly, you can practice with the free radicals. Okay, free radicals. At that time, you know, fish hook. Why? Okay, here is a electron, so fish hook, and it becomes free radicals, not positive. When positive is here, this hydrogen is plus. When free radical comes, this hydrogen is free radical. It is not given in NCERT book. Okay, that's why I explain. Okay, so the stability order of free radical is also in the same way. I just erase this. Methyl free radical is less stable than ethyl free radical is less stable than isopropyl free radical is less stable than tertiary butyl free radical is less stable. Okay, so which free radical is more stable? Tertiary butyl free radical. Tertiary carbocation is more stable. Similarly, tertiary butyl is more stable. And the same which is explained, the hyperconjugation is explained when the CH3 group is attached to the double bond. Okay, I just explain. You practice at home. For example, propene. Okay, propene. Double bond C, H. It's propene. The CH sigma bond is attached to the unsaturated system. Okay, the CH sigma bond is attached to the unsaturated system. As earlier, it is attached to the p or unshared p orbital. What happens here? If the electron is shifted to here and this bond comes into between the carbon atom, the hyperconjugative structure is H plus C, H, single bond C, H. The molecule is neutral, one positive charge and negative charge. When this electron comes into this, the carbon is negative and two hydrogen atoms is there. Okay, two hydrogen atoms are there. So here this hydrogen involved in the hyperconjugation. And this hydrogen involved, we get another hyperconjugative structure. This hydrogen involves one another hyperconjugative structures. So hyperconjugation, here is no bond. You can see that here is no bond. That's why it is called a no bond resonance. Hyperconjugation is also known as no bond resonance. Resonance effect is also known as mesomeric effect. Okay, I forgot to tell you. Resonance effect is also known as mesomeric effect. Plus M effect means positive mesomeric effect. Minus M effect means negative mesomeric effect. So these are the fundamentals in the reaction mechanism. What are the important fundamentals? Thing in the reaction mechanism? Homolytic fission forms of free radicals. Heterolytic fission forms carbocation or carbanion. Nucleophiles, nucleus loving species, they are negatively charged or neutral. Electrophiles, they are electron loving species, either positive or electron deficient. And displacement of electrons, inductive effect, plus I effect, minus I effect. Resonance effect or mesomeric effect, plus R effect and minus R effect. Then electromeric effect. Electromeric effect is a temporary effect. You remember that. Positive electromeric effect, negative electromeric effect. And the last one is hyperconjugation. It is also permanent effect. Hyperconjugation is a delocalization of CH sigma electron of alkyl group attached to the unsaturated system, or the carbon which contains unshared p orbital, or the atom which contains unshared p orbital. It is also known as Baker-Nathan effect and no bond resonance. Here you should keep in your mind inductive effect, resonance effect, hyperconjugation effect. These three effects are permanent effects. It is always in the molecule. It's a permanent effect. Electromeric effect is a temporary effect which works only in the presence of attacking reagents. Okay, these are very important concepts in the organic reaction mechanism. If you learn these things, you feel organic chemistry is an easy subject. Otherwise, you feel difficulties. So that's about this chapter. We successfully completed this chapter. The remaining portion is deleted from the syllabus. Okay. Purification of compounds and analysis. It's deleted. And the next section we will enter into the new chapter, hydrocarbons. A very simple chapter. So we will see in the next section. Thank you.